2 and the outline of my presentation which is going to cover the unit 4 wave shaping circuits and multivibrators. And very first, I'm going to start with the multivibrator circuits examples. That is the monostable multivibrator, astable and bistable multivibrator. And also, I'm going to cover this wave shaping circuit, that is Schmitt trigger. And this is the definition of this multivibrator. Before taking this multivibrator, just I want to tell you about this oscillator, because you all know aware of this oscillator. What is the oscillator? The oscillator means without giving any input, it is going to produces the output. Okay, that you know very well. So the same oscillator concept only we are going to analyze this multivibrator. In the oscillator, without giving any input, it is going to produces the sinusoidal signal, but this multivibrator is going to produces the non-sinusoidal signal. That means it is going to produces a square waveform or pulse or otherwise a rectangular waveform. So it is called as a non-linear oscillator or function generator, because you will be aware of this word function generator. What is a function generator? It is going to produce as the waveforms like a square waveform, pulse waveform and rectangular waveform. So that only this multivibrator is called as the function generator. And usually in oscillator circuit and the amplifier circuit, you will be using a single BJT. But in multivibrator circuit, we will be going to use 2 BJT or otherwise 2 FET circuits, and this will be arranged with regenerative feedback. And here I mentioned the types of multivibrators: astable multivibrator, monostable and bistable. Just I'll give you a short introduction about this types. Astable multivibrator. The circuit is not stable. Either state continuously oscillates from one state to other state. It is also called free running multivibrator. That means here the state. What is a state means? It is going to one state. One statement, either it will be a 0th state or 1, that is 0 and 1, both are the states. It will goes to one state and immediately it changes to 0th state, again it goes to one state, again it goes to 0 state. Likewise, okay, it will move, that is free, it is move from 0 to 1 and 1 to 0. So that's why it is called as the free running multivibrator. Then we'll take this monostable multivibrator. So from the word you can able to understand mono. Mono means in single. So single multivibrator. So the single state multivibrator. It will have only one stable state. The other stable state, okay, just we are calling it as a quasi-stable state. What does it mean? Quasi means it won't be stay there in that particular state. Immediately it comes to the next state. Okay, that is not a stable state. That's why we are calling it as a quasi-stable state. And the based on this definition, it is called as the one-shot multivibrator. In timer circuits, we can use this monostable multivibrator. And the third type of this multivibrator is bistable multivibrator. So the bistable multivibrator means bi means there are 2 stable states. So 2 stable state multivibrator. The circuit is stable in both the state and it will remain in either state indefinitely. The circuit can be flipped from one state to other state by an external event or a trigger. We should apply the triggering, then only the state will be changed. I will explain you elaborately in this session about this types of this multivibrator. And this bistable multivibrator, mostly it will be used in the flip-flop circuit. And okay, so we'll start the multivibrator concept. In the multivibrator, as I told, there are 2 BJTs. Okay, we are going to use. So the first, okay, if you are using a BJT means we should know about this transistor. You all know what is transistor? Okay, when how the transistor is going to be work. The transistor, base terminal, and it is having a emitter terminal, and it is having a collector terminal, 3-terminal device. Okay, and it is going to act as a switch. Okay, how it is? Okay, just see this diagram. Okay, in the diagram, I have given a common emitter amplifier diagram. Okay, and there are two cases will be defined in this transistor. The one is VI, that is the input voltage is less than 0.7, and VI is greater than 0.7. Okay, just I want to show you, okay, how the transistor is acts as a switch. Okay, so VI is less than 0 means 0.7 volts means the transistor is off condition. That means that the transistor is open condition. So if it is open condition means the collector current, okay, that will be represented by IC. So the IC value is equal to 0. Okay, and the VCE is equal to plus VCC. Okay, VCC is the supply voltage in the collector side. So VCE is equal to plus VCC. And when the transistor is greater than 0.7 means, the transistor is going to be switch on condition, and it is called as the saturation condition. What happens means the collector to emitter terminal is a short circuit, and the collector current, okay, just the collector is current is called as the IC saturation, and the VCE, that is the collector to emitter voltage, is very minimum. That's why VCE value is equal to 0. Students, okay, just to go through this slide very clearly, because this is the basic fundamental concept of this multivibrator analyzation. Because in multivibrator we are going to use the BJT circuit only, and especially, okay, the BJT when you are using means either the transistor in saturation condition, or otherwise, okay, the transistor is in the cutoff region, okay, cut-in voltage. Okay, so we are going to analyze saturation or cutoff. Okay, saturation or cutoff. Okay, this is the thing. Okay, just we are going to analyze in this session. And before start this Astable multivibrator, try to understand some of the terms in this transistor switching times. Now, okay, here left hand side the graph is given, and the first waveform is that is in between this time t1 and t2, a pulse is given, and you look on the second graph. The second graph, x-axis is your time, and y-axis is the ICC current. Okay, and the ICC current, okay, 0.1 IC saturation and 0.9 IC saturation, and if it is reaches 100% means that is equal to VCC divided by RC. Okay, from this graph, okay, just we are going to analyze some of the terms. Okay, so what are the terms? Okay, just to look on this x-axis, at that after the time t1, okay, next in small case, here I have mentioned td. Okay, the td is called as the delay time. Okay, and the next one is the tr is nothing but rise time. Okay, and after this t2 you can able to view this ts is nothing but storage time, and tf is the falling time. Okay, so td, okay, first you take the td and look on the graph. TD means the graph is slowly started and it goes to this 0.1 IC saturation. Okay, the same definition just we look on in the that is definition is given over here. The time that elapses during this delay, the time required for the IC to rise to 10% of its maximum value. Okay, so TD means that is the delay time at the time t is equal to t. Okay, just we can define, okay, the IC to rise to 10% of its maximum value. Okay, and the ICC saturation is nothing but VCC divided by RC. R means resistance and C means the capacitance. Okay, and the next time, okay, next time look on the graph once again. okay, where the TR is defined from 0.1 to 0.9, and here, okay, just to look on, okay, it is going to, that is the curve between 0.1 IC saturation to 0.9 IC saturation. So the rise time is defined as the time required for IC to rise from 10% to 90% of the maximum value. Okay, and the next the term is called as the turn on time. The turn on time is nothing but it is the combination of delay time and the rise time. Okay, next we are going to take this TS. TS is the storage time, and at the time t is equal to t2, just we can define this storage time, that interval which elapses between the transition of the input voltage waveform and IC has dropped to 90% of its maximum value. Again in the graph, okay, just you see the TS, okay, it is dropped to 90% of its maximum value. Okay, and next term is fall time. Okay, TF, the time required for IC to fall from 0% to 10% of its maximum value. Okay, so this is called as the fall time. Okay, and the next term is called as turn off time. Turn off time is nothing but it is the sum of the storage time and the fall time, that is called as the turn off time. So these are all the transistor switching times. Okay, and okay, we'll start this astable multivibrator. When you are taking this multivibrator concept, means first you be thorough this astable multivibrator, okay, and then okay, you just to go through this other multivibrator concept. Once if you understood, okay, astable multivibrator concept thoroughly, means you can able to analyze the other multivibrator concept very easily. Okay, so the definition, astable multivibrator. So it is going to generate a square waveform without giving any external triggering pulse. Okay, so see the explanation diagram here. We haven't given any input signal, so that's why no input. Okay, and it is applied to the circuit, that is astable multivibrator, and in the output, okay, just to go through it. Here I have mentioned the two states. The one state is stable state 1, okay, and the other state is stable state 0. That's why 1 and 0. Just to mark the states, okay, stable state 1, the next state is stable state 0. If it is goes to stable state 1, means that is plus VCC, and if it is in the 0, means okay, that is taken as the stable state 0. Okay, 1 and 0. Here these are all the two stable state, and parallelly I have mentioned the time also. When the stable state 1 is happening, means at the time t1, okay, and the next state 0 is happen in the time t2. So look on this diagram, it goes to one state and then 0 state, again it backs to one state, 0 state. So continuously you will be getting the output like this. That's why this astable multivibrator is called as the free running multivibrator. So free running multivibrator. Now, okay, we'll see elaborately the concept of this astable multivibrator. In astable multivibrator, just I am going to explain the three things. Okay, the first one is description. That is nothing but the operation of this astable multivibrator, followed by the waveform. Okay, how we are going to take the output. Okay, output is nothing but the collector output. Okay, because here we'll be using two transistor circuit. Okay, so we should analyze the outputs. Okay, so the second point is the output. Okay, that is the circuit output. Okay, the waveform analyzation, and the third one is okay, just how we are going to calculate the switching times. Okay, so in astable multivibrator, just you listen the how the astable multivibrator is working. Okay, so this is a very new circuit for you people. Okay, look on the circuit. Okay, so here we have used, there are two transistors, Q1 transistor and Q2 transistor. Okay, and this both the transistors are identical to each other. Okay, so just to look on the circuit connection in the emitter terminal of this Q1 and the emitter terminal of this Q2, both are coupled and it is given to the ground connection. Okay, and in a transistor, okay, the output, okay, in the output, okay, we have connected R1 resistance for Q1 and R4 resistance for Q2. So both are the collector resistance. Okay, so the collector resistance is here, it was mentioned as R1 and R4. In some of the places, okay, it was mentioned as RC, or in some of the places some other term will be given, that is like load also. Okay, don't be confused with the terms. R1 and R4 is the output, okay, that is the collector resistance, and it is the load resistance. Okay, and then, okay, the other two resistance, okay, here R2 and R3 were connected. The R2 is the base resistance and R3 is also a base resistance of this Q1 transistor and Q2 transistor. And here you note down, okay, VB1 is the base voltage of this transistor Q1, and VB2 is the that is the voltage, input voltage of this base voltage of this Q2 transistor. Okay, so this is the connection. And in the connection, just to look on one more important point, the transistor Q1 output, okay, the Q1 output is VC1, that is coupled through the C1 capacitance, and it is given to the input of this VB2. Okay, same like the same point we can give for Q2 output also. When you are taking this Q2 output of this Q2, VC2, the VC2 is coupled through the C2 capacitance to the input of this transistor Q1. Okay, so now you can understood, no, both the transistors are identical to each other. Okay, so that only in the point it was given as R2 is equal to R3 and R1 is equal to R4. Okay, and also both the capacitances C1 which will be equal to C2. Okay, and how to determine the frequency means we should take the RC time constant of the coupling circuit. Okay, and astable multivibrator. Astable means not stable state. Okay, not stable state means both the states are quasi-stable states. Okay, so quasi-stable state. Okay, now we'll come to just to look on this diagram again. Now I'm going to define the states. Okay, so previous slide I have shown you the two states, no, that is one state and another one is zero state. Okay, now I'll tell you the two states, okay, in the diagram. The first state one, the state one, we are assuming the transistor Q1 is on condition. If it is the Q1 is on means VC1 value is low. Okay, and in the next, okay, you can take this Q2 transistor. In the Q2 transistor, VC2 is high. Okay, so if it is high means, okay, the Q2 transistor is in the off condition. Got it now? And the next state, okay, just to take the vice versa condition, Q2 is on condition, so immediately VC2 is low. Okay, and the Q1 transistor is off condition and VC1, okay, the VC1 value is high. Okay, so these are all the two states. Okay, then two states, and the two states are quasi-stable states. Okay, and we'll start the operation of this astable multivibrator when we are powered the circuit. Okay, so powering means with the help of this VCC, okay, just we have to give the power. Okay, so VCC, okay, once it is switched on means, okay, what will happen? Immediately the voltage flow through the circuit, and due to the imbalance in the circuit components, okay, so in due imbalance in the circuit components means here we have connected resistors and capacitances. So due to this imbalance, what will happen means any one of the transistor will be switched on and the other will be switched off condition. So now you look on this diagram. Okay, here VCC is powered. We are assuming Q1 transistor is on condition and Q2 is in off condition. Okay, so with this assumption, okay, just we can start the analyzation. So as I told earlier, if Q1 is on condition means VC1, okay, that is the collector output of this transistor Q1 is low. Okay, so that low input is given through the C1 capacitance and it goes to the input of this Q2 transistor. So now the Q2 transistor is switched off. Okay, and if it is switched off means VC2, the output of this Q2, okay, that is the VC2 is high. Okay, and that high input is coupled through the C2 capacitor and it is given to the input of this Q1 transistor. Okay, so the Q1 transistor is on condition means, okay, so this is the thing will be happen. So as I told earlier, okay, state 1 means Q1 is switched on, VC1 is low voltage, that low voltage is given to this Q2 transistor, Q2 transistor is off condition, then VC2 is high and the high input is given to through the C2 capacitant, it is given to the input of this Q1 transistor. Okay, so this is the thing is happening in the circuit. Okay, so how long it is going to be happen? Okay, because here we have connected C1 capacitance and C2 capacitance. What will happen? C1 capacitance will be charged through the R2 base resistance and C2 will be charged through this R4 resistances. Okay, so now you just to look on the circuit. Okay, here the blue color line, okay, the voltage flow is given for VB1 and VB2. VCC is given through this R3. Okay, the flow is given to this VB1 circuit, and again the other side, okay, VCC is provided means the flow is given through this R2 and then it reaches to the input of this Q2. Okay, so this is the first state. Okay, so in the first state what we assumed means Q1 is charged and Q1 is on condition and Q2 is off condition. Okay, and the capacitance C1, okay, this is in charged condition and the charged condition will not be remain in so longer. Okay, it has to discharge and the same time the discharged condition in C2 is going to be changed into charging condition through the resistance R4. Okay, got it? Okay, first we are taking the state 1. In the state 1, okay, we will be assuming one transistor is on, the another transistor is off, and after that we are going to take the analyzation of this capacitances. C1 is going to be discharged now, okay, and C2 is going to be charged now. Okay, so charging of the C2 is happen through the resistance R4. So the through this resistance R4, if the charging will be happen means, okay, look on the polarity of the C2. One end of the plate is positive, the another end of the plate is negative. So the negative, okay, that is the minus VCC is given to the input of this transistor Q1. You got it? So it is the slightly we are reducing the base voltage, and at the same time, okay, you take the concept of this discharge of this capacitance C1. So discharge of this capacitance C1 means the one end of the plate is positive, the another end of the plate is negative. Okay, now the status state 1 condition, Q1 is an on condition. So on means the collector to emitter terminal is short. So this positive is directly connected where it will goes. Okay, this positive, see here. So this positive is directly connected to the emitter terminal. Okay, so this is what happening in this charging and discharging condition. Okay, briefly, just to look on the circuit diagram of this charging and discharging of this capacitances here. So in the first diagram, C1 is discharging, and the time period here it is given as T1 is equal to R2 into C1, and C2 is charging, T2 is equal to R4 into C2. Okay, and the discharge of the C1, the blue color line, it was mentioned here. The line is drawn from the VCC through this R2, C1 discharging. Okay, and it is given to the through this Q1. Okay, and same like here charging of the C2 is happened through to the R4 and the C2, and it is given to the VB1 of this Q1 transistor. Okay, and just to make the comparison between this charging and discharging period. Okay, in the center it was given here time taken to discharge of C1. Okay, always it should be greater than the time taken of the charging of the C2. Okay, and I already told you, okay, the VC2 drop will be occur in VC2. The capacitance C2 will be charged via this R4, and this path is called as the low resistance path. Okay, the low resistance path means just we are making the comparison between this R4 and R2 resistance. R4 is less than this R2. That's why this path is called as the low resistance path. And same like, okay, if the C1, okay, starts discharging via R2, and this path is called as the high resistance path. Okay, why it is called as the high resistance path means R2 value is greater than the value of this R1. Okay, so this is the case will be happen. Okay, when you are taking the transistor Q1 is on and transistor Q2 is off. Okay, so and after that what happened means the C2 is fully charged, then the left plate of the C2 will be at minus VCC. So what happens with switch off the Q1 transistor? Okay, as I told earlier, the parallelly, okay, just we have to look on the discharging of C1 condition also. So the transistor Q1 is on condition means a short circuit, collector to emitter terminal will be short circuit. Okay, and the C1 is fully discharged. The left plate of the C1 will be a plus sign. Okay, you can able to view in the diagram. So the plus, okay, supply VCC supply is given directly to the emitter terminal of this Q2. Then Q2 transistor is on condition. Okay, got it? Okay, so initially we are keeping the transistor Q1 is on. Okay, and Q2 is off. Okay, and after that, because of this charging and discharging of this C1 and C2 capacitance, what will happen? It changes the state to another one. Okay, that is it goes to Q2 goes to on condition and Q1 goes to off condition, and this process will be repeats. Okay, on to off to on. Okay, and once if you understood the basic concept of this Astable multivibrator means it is very easy to analyze the type of this Astable multivibrator. Okay, so the type means there are two types in Astable multivibrator. The one is called as the collector coupled Astable multivibrator, and the another one is called as the emitter coupled. Now from the name itself you can able to understand the concept. Collector coupled, okay, the coupling is given in the collector side. Okay, that's why it is called as the collector coupled Astable multivibrator. When the coupling is given in the emitter side means that is called as the emitter coupled Astable multivibrator. So here we'll take the example of this collector coupled Astable multivibrator. The same operation, okay, already we discussed in Astable multivibrator. Again, you look on this diagram. Okay, in the diagram there are two transistors, Q1 and Q2 transistor. Okay, and the coupling. Okay, the coupling, look on this transistor output is the collector terminal. The collector terminal is coupled through the C1 capacitance to the input of this Q2 transistor. Same like Q2 output is coupled through this C2. Okay, and it is given to the input of this Q1 capacitance, Q1 transistor. Okay, and other things as I told earlier, RC1 and RC2 are the collector resistances, and the base resistance, which will be denoted here as RB1 and RB2. Okay, and when we are giving the input means we have to take the first state, and after the charging and discharging of the capacitance, it change the state to another state. Okay, and in this circuit diagram, okay, one more thing, just I want to give. Okay, the transistor means, okay, it can able to produce as a 180-degree phase shift. Okay, so here we are using two transistors. The total phase shift here it is 360-degree. And once if you are providing a positive feedback means the circuit will act as a oscillator. Okay, and the both the transistors are NPN transistor, and here we are using two common emitter amplifying stages. Okay, and the remaining things, RC1 will be equal to RC2, RB1 is equal to RB2, C1 is equal to C2. That's why we are calling two identical transistors. Okay, so again the same concept only. Now, okay, we'll see the output of this collector coupled astable multivibrator. Look on the diagram. In the first diagram, VC1 output is drawn. The next one is VBE. The next one is VC2. Okay, first, and you look on the x-axis and y-axis. In x-axis, okay, you can be able to view 0, T1 and T2. Okay, when the time is at T is greater than 0, T is equal to T1 and T is equal to T2, we have to analyze the circuit condition. First, initially, just we are assuming Q1 is on and Q2 is off, T is greater than 0. Now, first you take, initially you take T is greater than 0 means before T1, okay, just to take the period. Okay, and here T is greater than 0 means what will happen? Okay, Q1 is on and Q2 is off. VB1 is VB saturation, and it is 0.7 volts is for silicon, and the VC1 is equal to VCE saturation. Okay, so in VC1, okay, that in the that is a small voltage, okay, VCE saturation will be given, and at the same time you look on this third output. Okay, in the third output VC2 is given. What is VC2? VC2 is equal to VCC. Okay, you can able to view. Okay, it is in the high, that is high state. Okay, on state condition. Okay, and during the time, okay, that is T is greater than 0, we should look on the charging condition also. As I told earlier, C1 is charging towards the voltage VCC through the R1 resistance. So the charging takes place exponentially. Okay, so the time constant tau is equal to R1 into C1. Okay, and the base of this Q2 is directly connected to the C1. So VB2 is also increases exponentially towards VCC. Got it? Okay, and next, okay, we'll go to the next time. Okay, next time period means, okay, the time T is equal to T1. Okay, and at that time the VCC is equal to VCC minus VCE saturation. The rise in VC1 is coupled through the C1 to the base of Q2, and it causes small overshoot voltage in this VB2. Just to see in the second graph, the small overshoot is drawn here. Okay, and if the time period is greater than or equal to T1 means Q1 is switch off condition. Then at that time, okay, see in the first output VC1 is equal to, now it is equal to VCC. Okay, and take the last graph in the output of this VC2. Okay, that is equal to VCE saturation. And here also we can define, okay, at T is greater than T1, just we can define the time constant tau 2 is equal to R2 into C2. Okay, so just we are taking T is greater than 0 at the time T is equal to 1. Okay, and if the time T is greater than T1 and the next time is T is equal to T2. T is equal to T2, VB1 reaches the cut-in level and the reverse transition takes place now. So Q1 is turns on condition and Q2 is turns off condition. So this is the way just we have to analyze the output waveform of this astable multivibrator. So in the astable multivibrator, we'll be having the outputs VC1 and VC2 parallelly. Just we have to look on this VBE output also. So while you are analyzing this output, okay, just to take the period, okay, with the reference of the period, okay, once if you are analyzing means it is very easily to understood, okay, the concept, okay. So this is the first, we have seen the description, and the second one we analyze the output, okay, and the third thing, okay, that is the very important one. The next one is switching. That is switching times, okay. So the calculation of switching times and the frequency of oscillation, this is very important, because when you are designing a stable multivibrator, we should aware of this, the calculation of the switching time and the frequency of oscillation, okay. And you know, okay, in the first diagram, okay, here I have mentioned, okay, the voltage flow of this voltage flow of this base to the Q1 transistor and Q2 transistor, okay. Just to remember that, okay, from that only just we are writing the first equation. VB2 is obtained by Kirchhoff's voltage law to the input of this Q2. So VCC is equal to the drop across this RB1, okay, resistance is IC1, that's why IC1 into RB1 plus the voltage drop is VB2, okay. So from this equation only just you can able to calculate the time, okay. So in this equation, just to rewrite the equation, VB2 is equal to, and after that, okay, we have to define the IC1 value. The initial discharge value of this current IC1, which will be equal to VCC plus VCC divided by RB1. So that is equal to twice the time of VCC divided by RB1. And also the capacitor charge up to VCC, and the current decays exponentially by a time constant of RB1 into C1. So that's why the IC1, which will be defined by 2 into VCC divided by RB1 into e to the power of minus t divided by RB1 into C1, okay. And you have to assume, okay, the transistor is switched off condition, VB2 value will be equal to 0. So make this VBT is equal to 0, and also substitute this IC1 value in the first equation, okay. So make this VB2 value is equal to 0 and substitute this IC1. You can able to view the second equation, and in the second equation, okay, just to take the common term VCC out, you will be getting this equation. Again, you reduce this equation, you will be getting the time period T is equal to RB1 into C1 into natural logarithm of 2, okay. So in the previous equation, you can able to view the exponential term e to the power. How to cancel it means we should take the natural logarithm in LHS and RHS, okay. That's why it was given here as, okay, T is equal to RB1 into C1 natural logarithm of 2. Got it? Okay. So from this, okay, just the answer value of this natural logarithm of 2 is given, okay, that is T is equal to 0.693 RB1 into C1, okay. And same like we have to calculate the other transistor also, okay. So the off time of this Q1 and the off time of this transistor Q2 can be obtained by T1 time period and T2 time period, okay. And the overall time period, okay, that is capital T is equal to small t1 plus small t2, okay. Just to combine both the thing, okay, sum of the both the things will be given in this equation, okay. Now you take the assumption RB1 is equal to RB2, that is equal to R, and same like the capacitance, okay, C1 is equal to C2, okay, that is equal to C, okay. Just to take this approximation in the equation. So it is R into C, okay, and you have to take the consolidation. So T is equal to 1.4, okay, R into C. Okay, and the next equation you can able to view the frequency. It is inverse of the time period, so it is equal to 0.7 into RC. Okay, so just to remember this switching calculation while we are doing the design. So in the Astable multivibrator, the first thing I have explained you about this description. Okay, in the description, just to remember only 2 points. Okay, when we are powered, the circuit means, okay, one transistor is on, the another transistor is off, and how to change this statements. Okay, we have to give a charging and discharging concept. Okay, then we'll be obtaining the next state. Okay, and then we'll be taking the circuit output. Okay, that is with the help of this VC1 output and VC2 output and VBE, just we can able to understand. And the third one is the calculation of the switching time and the frequency of oscillation. Okay, and the next type of this multivibrator is monostable multivibrator. The word mono means it's a single. Okay, so single stable multivibrator, only one stable state. Okay, and simply for explaining the concept, okay, look on the diagram here. The input is we'll be giving only one trigger signal. Okay, that is T1 to the monostable multivibrator. In the output side, okay, just we'll be able to see there are two levels, minus V out and plus V out. Okay, once if you are providing trigger, okay, T1 means what will happen? The state, okay, from minus V out is changed to the plus V out. Okay, and after some time the circuit automatically reverts to its original condition and remains in that way until another trigger pulse is applied to the circuit. Okay, so this is the basic concept of this monostable multivibrator. Got it? Okay, and I'll explain you about the circuit operation. Okay, so just to look on the circuit. Okay, Q1 transistor and Q2 transistor. Okay, and the concept of this monostable multivibrator is we'll be going to provide a single state only. That's why, okay, one of the coupling, okay, path is removed over here. Okay, just to look on this diagram, the Q2 output, okay, the Q2 output VC2, okay, that coupling is removed. Okay, and we'll be having only one coupling, okay, in the Q1 transistor. So in the Q1 transistor output C1 is coupled to the coupled through the C1 capacitance to the base of this VB2. Okay, now we'll see the concept of this triggering. Okay, so the triggering, where the triggering was applied, okay, look on the diagram, it is applied in the Q2 transistor, and the triggering pulse also I have mentioned here. First high state, and after some time, okay, this will be changed to ground state. Okay, so first if you are applying a trigger, external trigger means what will happen? Okay, the external trigger is connected to VB2. So VB2 will charges the up to VCC voltage. Okay, and that is it can able to produces, okay, the voltage to tune on the transistor Q2. Okay, so VB2 is on means the transistor Q2 is switched on. Okay, and the output of this VC2, okay, that pulls the a transistor on condition to off condition. Okay, so got it? Okay, first initially we will be assuming when you are giving the VCC means always, okay, we'll be assuming Q1 transistor is on and Q2 transistor is off. Okay, and in the monostable multivibrator, with the help of this triggering, input triggering, okay, that is if it is high means, okay, the next state, okay, Q1 transistor will be switched on, okay, and VC2 is low and it makes this Q1 transistor to off condition. Okay, and this is the state 1. Okay, and how to switch to the next state means, again you look on this triggering pulse. Okay, now we are taking the VB2 pulled to ground by an external triggering. So now the transistor Q2 is off and VC2 rises. Okay, that is high voltage and it rises the VB1. So transistor Q1 is switch on condition. Okay, so this is what happening, and if it is switch on condition means VC1 is equal to 0 and it pulls off this Q2 transistor to off condition. Okay, so this is what happening in monostable multivibrator. In monostable also, the first thing is to remember, when we are powered, this VCC means Q1 is on and Q2 is off. The second point, we are giving the triggering input. Okay, the triggering input initially assume it is high. When it is high means, okay, VB2 is on to turn on this Q2 transistor. So Q2 is on, and at the same time the output of this VC2 is low. Okay, and Q1 transistor is off. Okay, this is the next condition. And after that, what happened? Okay, VC2 is, okay, through the coupling, okay, it is given to Q2 transistor. Okay, and again we can change the triggering from high to ground, or ground to high means, okay, this will goes. Okay, that is the, with the help of the triggering only it changes the state. Okay, and the time period here also T is equal to 0.69 into RC. Okay, and just to look on the output waveform. Okay, in the output waveform, the first signal is VC1 output and the second signal is VC2 output. Okay, and the small voltages VCE saturation is also mentioned in this waveform, and the third one is the trigger input. First you look on the first pulse. The first pulse Q1 is off and Q2 is on. Now we want to change the trigger. Okay, that is, we want to change the statements. Okay, we have to give the trigger input. Okay, so when we are providing this trigger input, what will happen? Q1 transistor is switched on condition and Q2 transistor is switched off condition. Again it goes back to the original question. Again, once if you are providing another trigger input means this will change the state. Okay, so this is the concept of this monostable multivibrator. Okay, and the application of this monostable multivibrator, it is used as it is used in delay and timing circuit. Temporary memories also we can use it, and it is often used in trigger another pulse generator, and it is also used for regenerating old and worn out pulses. Okay, so these are all the application of this monostable multivibrator. Okay, and the next type of this multivibrator is bistable. Okay, so now I'll explain you what is a bistable multivibrator. Bi, okay, the word bi, what is it? Okay, that is two stable state. Bi means two. So in a bistable multivibrator, there are two stable state. Okay, and look on the diagram in the first graph. Okay, stable state 1 and stable state 2, and again stable state 1, okay, is given. And in the second waveform, okay, you can able to view two trigger pulses. The transistor is in stable state 1. Okay, when we want to switch the stable state 1 to stable state 2 means we have to apply the first trigger pulse. Okay, immediately stable state 1 is switched to stable state 2 and it remains in the same stable state only. And again, okay, if you want to switch stable state 2 to stable state 1 means we have to give another trigger pulse. So what will happen? Stable state 2 is switched to stable state 1. Okay, so this is the concept of this bistable multivibrator. Okay, and we'll see, okay, briefly the concept of this bistable multivibrator with the help of this circuit diagram. Look on the circuit diagram. There are two transistors, Q1 transistor and Q2 transistor. Okay, and the output of this Q1 transistor, RL1 resistance, and here Q2 transistor output. Okay, here we have connected RL2 resistor. Okay, and both are coupled to the VCC. And the point, okay, Q1 transistor, okay, the point A, okay, the R1 resistance is coupled to the base of this Q2 transistor, same like the output of this Q2 transistor, the point B. Okay, you can able to view the point B, and it is connected through this R2 resistance, and it is connected to the input of this Q1 transistor. So the coupling, okay, just you look on the path, Q1 output A through the R1, okay, it is given to the input of this Q2, and same like Q2 output is given to the input of this Q1 through the R2 resistance. Okay, and also here you can view that R1 and R2, okay, both are shunt with the capacitance C1 and C2. So the C1 and C2 capacitance is called as the commutating capacitor, and it is employed to improve the switching characteristics of the circuit. Okay, and other than this, okay, here you see, okay, we are going to take the two stable state. Okay, so previously, okay, in monostable multivibrator only one stable state, that's why we'll be giving a single external trigger, okay, in the Q2 side. Now, okay, we are going to take two stable state, so that's why we'll be in the need of two triggering pulses. Okay, so that only in the base of this Q1 input 1 through the C3, okay, it is given the first trigger, and look on this second transistor side, okay, we'll be giving the second trigger input, okay, through this C4. Okay, and other than this, the base resistances R3 and R4 is coupled to the minus VBB. Okay, and this is the circuit description. Okay, in the circuit description, just to remember one thing, okay, the output of this Q1 is coupled through this R1 to Q2 transistor, and the Q2 transistor output is coupled through this R2 to the Q1 transistor. Okay, so now we'll take the concept. Okay, the Q1 transistor is on. Okay, so initially the same condition only. Okay, when we are powered the circuit, okay, VCC is given. Okay, any one of the transistor has to be switched on. So we are assuming Q1 is on condition. Okay, and if Q1 is on means, okay, at the point A, okay, that is the output of this Q1, okay, that is very low. Okay, and the low input voltage is given to this transistor Q2. So what happens, Q2 is switch off condition, and again this output of this Q2 is given back to this Q1 more saturation. Got it? Okay, so this is the first condition. The first condition, okay, Q1 transistor is on. Okay, just to look on, Q1 is on and Q2 is off condition. Okay, and when we want to change the state, okay, so now Q1 is on and Q2 is off. Okay, when we want to change the state means we have to provide a positive triggering in the Q2 transistor side, or otherwise we have to provide a negative triggering in the Q1 transistor side. Okay, so when we want to change the state, okay, that is Q1 and Q2 state means we have to provide, okay, external triggering. Now we are assumed Q1 is on and Q2 is off. Okay, now we want to change the state. Okay, so we will be providing a positive trigger in the Q2 transistor side. So if you are providing positive trigger means what will happen in the transistor Q2? The Q2 transistor is going to be conducted. It is going to be switch on condition, and the output of this Q2 is low, and the low output is coupled through this R2 resistance and is given to the input of the transistor. Okay, and this is the input of the transistor. If you are giving means what will happen, the Q1 transistor will goes to off state. Okay, so this is what we are changing the state of this Q1 on to off state and Q2 off to on state. Okay, so this is the first state change. Okay, Q1 is on and Q2 is off. Okay, next state is Q1 is off and Q2 is on. Okay, so now again come to the circuit. I already told you Q2 is on condition. Okay, the output of this Q2 is, okay, very low. Okay, and the low input is given to this Q2, and it is okay, off condition. Okay, how to change this condition means we have to give a positive triggering in the Q1 transistor side, or otherwise we should give a negative trigger in the Q2 transistor side. Okay, simple concept, vice versa condition only. Okay, previously what we did, the second transistor side, okay, we have given the trigger. Okay, now we have to give, okay, the trigger in the first transistor side. Okay, so now we want to change the this state, okay, Q2 transistor to switch off condition. So in the Q1 transistor side, will be giving a positive triggering. So the positive triggering will induce the transistor Q1 to on condition. So if it is on means at the point A, okay, a minimum voltage drop, and this turns the transistor Q2 to off. Okay, so this is what, okay, we are taking the second state of this bistable multivibrator. It is a very simple concept. Okay, once if you understood Astable multivibrator means it, you can easily understand this bistable multivibrator, because in bistable multivibrator, with the help of two triggering pulses, we can take the stable states. Okay, a stable state to one stable state to another stable state. Okay, and this is the output of this bistable multivibrator. The first pulse Q1 is on and Q2 is off. We want to change the state. That's why trigger input 1 is given. What will happen? Q1 is off and Q2 is on. Okay, and after this, okay, we want to change the state again. Okay, so we have to use the second trigger input 2. Okay, when we are giving means what will happen? Q1 off condition to Q1 on condition, Q2 on to off condition. So this is what, okay, we are using two triggering pulses in the bistable multivibrator. And the applications, it is mostly used in the digital operation in computer and a digital communication, and it is also used for reversing to the supply to a given circuit. Okay, and this is the application of this bistable multivibrator output. Okay, and the next one, okay, will take this wave shaping circuit. What is a wave shaping circuit? Once if you are given a sinusoidal signal means the sinusoidal signal will be converted into a square waveform. Okay, just we are shaping the circuit. Okay, so with the help of the Schmitt trigger, okay, just we can make the concept. Okay, and before start this Schmitt trigger, just I want to take a small concept, okay, of this comparator. What is meant by a comparator? The comparator means, okay, comparator, the word, okay, if you are giving two input signal means it is going to produces the output signal with the reference of the voltage inputs. Okay, and the two inputs, okay, just to take V1 input, the another input is V2. Okay, and we are considering V2 as the reference. Okay, so if suppose in the comparator the V1 will have more noises, okay, what happened in the output of this comparator circuit? Definitely the noise will be affected in the output also. So to rectify this problem, okay, we will be taking this Schmitt trigger. Okay, so the Schmitt trigger is nothing but a comparator circuit with hysteresis. Okay, so that the output transition from high to low and low to high will occur in different threshold levels. Okay, so the Schmitt trigger is an electronic circuit with a positive feedback which converts the sinusoidal or any analog signal into a digital signal. Okay, and it belongs to the class of this bistable multivibrator only, which have two opposite operating states. Okay, and the Schmitt trigger here, and the second point here, it was given no high to low and low to high. Okay, and you can refer the two triggering levels as LTL and UTL, lower triggering level and upper triggering level. We can call the tree, instead of call this trigger, we can put the word threshold also. So upper threshold value and lower threshold value. Okay, and see that circuit diagram here. That two transistors Q1 and Q2 were connected. The output of the transistor Q1 is coupled through the R1 and it is given to the input of this Q2. And if you are giving, okay, if you are giving very low voltage means VI value is very, very low, and at the time, okay, what will happen to this Q1 transistor? The Q1 transistor is off condition, and you look on this VCC supply. The VCC supply is given. I have marked a dotted lines over here. It will flows through this R1, RC1, R1 to R2, or otherwise through this RC2. It will flows. Okay, and when we are taking this resistance RC1, R1, R2 means it is a potential divider circuit. So the voltage across this VB2 will be equal to R2 divided by RC1 plus R1 plus R2 into VCC. And when you are providing this the VCC supply, okay, the current flow across this RC2 is IC2. So the IC2 is flows, okay, in the RE resistance. So here VE is equal to RE into IC2. Okay, so this is called as the upper threshold point. Okay, and the next one, if you are applying more input voltage means, okay, the transistor Q1 is on, and at the same time, okay, if you are looking the current across this RE means that is IC1. So the lower threshold point is VE dash plus VB1. Okay, so this is lower threshold point. Okay, so the working principle of the Schmitt trigger is given. Okay, what I have explained, the same thing will be given over here, and see the waveform output. Okay, the input is sinusoidal signal. If it is takes this upper threshold point means the transistor will be off condition to on condition, and if it is lower than this lower threshold point means what will happen, the on condition of this transistor Q1 will change it into off condition. So this is what we can get the square wave output. Okay, and the application of the Schmitt trigger is given over here. It removes the noise signal in the digital circuit. It is used as a squaring circuit, and it is used amplitude comparator or level detector, and it is used as the flip-flop circuit, and it is used for reshaping circuit. Okay, thank you. So this